get started. So the first lecture is kind of like an introduction, but it also covers some material. Okay. So first is about what algorithm class is. Okay. So this algorithm class, as I said, okay, we consider it to be a theoretical study of computer program performance and the resource usage. Okay. So obviously this is important, right? Because in computers, I mean, we always write a program for computers. So it's obviously the program performance is important. And also like the resource used by your program is also important. Like, they are important factors. But there are other important factors, other than the performance. For example, modularity, correctness, maintainability, functionality, robustness, user friendliness, programmer time, how much time it take you to develop the program, or simplicity, extensibility, reliability. All these factors will not be considered in this class. Okay, they are considered in other classes. Okay, for example, okay, like modularity, functionality. Okay, I mean those factors may be considered by the software engineering class. Okay, so user friendliness may be considered by like HCI, human computer interaction. Okay, so there are a lot of like factors. Okay, that are important. So performance obviously is also important, but the other factors are, also they are also important. Okay, so we only consider this performance aspect of the computer program in this class. So why do we study algorithms and their performance? Algorithms help us to understand scalability. So this is important. Okay, scalability. Like when your idea work on a small problem, small size, okay, you need to know if the same approach work on the same problem of large size. Okay, so so performance, draw the line between what is feasible and what is impossible. I mean, your approach may work for maybe like just a few instances, but when it comes to like a large, the same problem, large size, your approach may fall apart. Okay, so that is like where this class is about. Okay, we need to make sure, okay, your program, your algorithm design, is scalable. Okay, it didn't just work for like small program, small size problems. So algorithms, mathematics, provide a language for talking about program behavior. Okay, so it is also, you can also consider algorithm as a language. Okay, as I will show you later. Okay, when I say language, there are actually two levels of two different meanings. Okay, the first one is the pseudocode. Okay, we will use pseudocode to discuss the program, algorithms a lot. So that's like a common language across different disciplines. The second thing is like mathematically, you use like some like notations. Okay, we discuss like the performance or put it in a more concrete way, the complexity of your algorithm. Okay, such as big O notation, like theta, omega, those like notations. Okay, they are also considered, language. Okay, we're talking about programming language. Okay, and the performance is a currency of computing because like this is especially true when it comes to a GPU. In my lab, like we have to like purchase like a credit from like I don't know if you know about this service called Vast.ai. Okay, they provide like a lot of GPU resources to like to subscribers, but the better GPU you use, the more time you use, they charge, the more they will charge you. Okay, so obviously, if your program has a better performance, okay, you save money. So when I say currency of computing, I literally mean money. Okay, here. So let's say program performance generalized to other computing sources. This is like remember like at the beginning here, we are talking about computer performance and the resource usage. So what would be the resource that is considered here? For example, memory. Okay, how much memory does your program, does your algorithm require? Okay, and there are also other uses, but usually we only consider time and memory, okay, in our class. There are other resources, obviously. Okay, for example, it's like a multi-process situation. Like a lot of time you use message passage. Okay, between different processes, and like sending a message from one process to another take a lot of time. Okay. So we also need to consider like how many message passes, okay, your algorithm, require. But yeah, that is usually considered in like a parallel computing, okay, but not this class. Okay. In this class, we usually consider only one CPU, okay, one computer, okay. And obviously the best reason, okay, for this class is speed start. Okay, the faster the program, the better, right? So to keep a good illustration, okay, so we need to consider one like important problem. You can say it's probably one of the most important problems computer program, okay, which is the sorting problem. In the sorting problem, okay, you see a lot of places that make use of the sorting. Okay, so in database, in like as long as you have some jobs that you need to consider the priority, it's always about sorting. Okay, so in the sorting problem, you are given a sequence. So A1, A2, blah blah blah, AN, some numbers, and your output will be a permutation of these numbers. And this permutation, okay, you have to guarantee, okay, the A1 prime small or equal to a2 prime, small or equal to blah, blah, small or equal to an prime. I'm sorry. So, one example that I can give you, for example, inputs A24936. So the output will be 2, 3, 4, 6, 8, 9. Okay. There are a few things that some details that I would like to think about. First, if these AIs are different, then this permutation is unique, right? So, 如果这些数字都 sorry, okay, I sometimes I'm resorting back to Chinese just to make sure that all the students fully understand. Okay, 就是如果所有数字都不一样，你那个 permutation 的结果，就是 sorting 完以后 permutation 的结果，应该就是唯一的嘛，对不对？ Oh, by the way, here we are talking about ascending, and order. We list them from the smallest one to the largest. Okay. Sometimes we also consider descending, sorting the number in descending order. So in that case, like we will list the numbers from the largest one to smallest one. Okay. But anyway, let's stick with this one. Stick with like the ascending order. Okay. So then if the numbers are different, obviously you only have one answer. But if some numbers are the same, okay, then okay, your answer is not unique, right? This permutation is not unique. 我就举个例子来讲 ，Let me give you an example. Say, if you have two, three, maybe let's change this A to 3. So you have 3, 2, 4, 9, 3, 6. Okay, for clarification, let me mark this 3 as 3, 1. This 3 as 3, 2. Okay? Then the result will be 2, 3, 3, 4, 6, 9, right? But it could be 2, 3, 1, 3, 2, 4, 6, 9. Or it could be 2, 3, 2, 3, 1, 4, 6, 9. You know what I'm saying? 就是如果说你有两个数字是一样，或者甚至更多的数字一样，它那个排列出来的那个 permutation is not unique. The permutation is not unique. Okay, so there are also we sometimes also need to consider sorting algorithm. In situation like that, we need to guarantee, for example, like if some numbers are the same. For example, given like this 3, 1, 3, 2, we need to make sure 3, 1 always appear ahead of 3, 2. Okay, because in the original list, 3, 1 appear ahead of 3, 2, right? So in your output, like the 3, 1 has to appear ahead of 3, 2. Okay, if your sorting algorithm consider that or not. Okay? Anyway, let's just forget about those details. Let's just imagine you have different numbers. Okay, let's consider simplest situation. Okay? So, the first, or put it another way, this, I would like to use the word like simplest. Okay, sorting algorithm, but I'm not sure. Like, maybe some of you have learned this insertion sort from different other places. Okay, how about data structure class? In the data structure class, like, you have learned insertion sort, right? Did you learn bubble sort? Bubble sort. Good, good, good. I mean, we will not cover bubble sort. Okay. We only talk about insertion sort. How about merge sort? Merge sort. Okay, good. So then, I mean, that's good. Because in this chapter, we are going to consider insertion sort and merge sort. So if you guys know about this tool, then it makes our job easy. Okay, we can quickly go with 2LB. Okay, so the pseudocode of the insertion sort looks like this. So first is the concept of pseudocode. When we discuss algorithm, we tend to use pseudocode. And in the pseudocode, you can see that, okay, you write your algorithm in a form of function. And you can specify the input, the output, similar to a function. And you have like the construct, such as for, do, while, just like you are writing a program. But the style, okay, may be different from some programming languages, but that's fine. Just stick with like one pseudocode like format, okay, to make sure you fully understand what we are talking about here, okay. And if you know the insertion sort already, so here I mean it's a quick review for you, okay. So for J from 2 to N to blah blah blah. Basically, insertion sort is like this. Let's assume that the first part has been done, has been sorted. Now we're going to insert one additional part, additional number into this sorted list. So we find the right place for this number. Okay, that's it. Okay, that's the basic idea of the insertion sort. So one quick question is, so why J start from 2? Because when you have only one number, it is impossible that number is not sorted, right? Okay, so that's why when you want to insert the number into a sorted list, you start from the second number, okay? And so let's have a look. This is exactly the idea, okay? Basically, assuming this part has been sorted, now we consider inserting one additional number. So we try to compare this number with these numbers. So if this new number is smaller than these numbers, so we will move these numbers one position to the right. Okay, until we find some numbers are smaller than this one. So we stop and insert this number. So that's the right place for this number. So after that, this part has been sorted, right? So we consider one additional number, something like that. So this concept of programming the algorithm design is called incremental design. Because each time you increase the problem size by 1. Okay, you have a sorted list, and then you add one additional number to it. You make a longer sorted list, and so on. So this is considered in terms of the algorithm design paradigm. It is considered incremental algorithm design. So let's have a look at what this insertion sort really does for us. Okay, so at the beginning, okay, we have these numbers. So J start from 2, right? Remember? So J is the indicate that the number you would like to insert. Okay, so you can see that 2. Okay, I mean, of course, as I said, A. If you have only one number, it is already sorted, right? 8 is already sorted. So Now you want to insert 2 to the sorting list. So obviously, 2 is smaller than 8. So what happens is that 2 will be inserted ahead of 8. So 8 will be moved 1% to the right to clear the space for 2. So that is what happens. Okay, so you will end up having 2, 8. Okay, so the first 2 has been solved. Okay, and then J moves to 3. You try to insert the third number into the previous 2 this sublist. And then you compare 4 with 8. You find 4 is smaller than 8, so you 8 is moved 1% to the right. And then you compare 4 with 2. Well, 4 is greater than 2, so you know that 4 should be inserted in between 2, after 2. Okay, so that is where you put it 4. Okay, so the result is 2, 4, 8. And then you keep considering, okay, now you insert 9. So you compare 9 with 8. Well, 8 is already smaller than 9, so nothing needs to be done. Stop. And then you just keep it there. And then you consider adding 3, 3 obviously will be inserted here. So all these numbers will be moved 1% to the right. No. And then last one, you insert 6. Then you are done. Okay, with these numbers. So that's the idea of insertion. So first, the concept is incremental algorithm. Okay, and obviously, depending on where you insert this new number, you will, there will be a certain number of movements, right? Certain number of movements. Plus 1, because eventually you will move new number to the right position. So, how about running time? So the running time of the algorithm depends on the input. Of course, like an already sorted sequence is easier to solve. Okay, so think about this. If the input is already sorted, then every number is already in the rightful place. Then you don't need to move anything, right? But you still need to have some comparison, right? Every time you try to insert 1, well, it's already at the right place. So you need one comparison. But at least it's much faster, right? You don't need to move any number. So yeah, your input will affect the running time. Okay, that's for sure. Okay. So another thing that influences the running time is the size of the problem, right? Inserting, sorting like a finite, obviously the time required to sort finite is different from the time you require to sort like a million numbers, right? So you should parameterize the running time by the size of the input. Okay, because the short sequences are easier to solve than long ones, obviously. Okay. So generally we seek upper bound on the running time. Okay. Because we like to have a guarantee. Okay, upper bound. Okay. What do we mean by upper bound? That means the worst case analysis. Okay. For a fixed size of the problem. For a fixed size of the problem, we consider what situation will let this algorithm execute the this time. So that is what we call worst case analysis. That is usually what we do. So Tn will be the maximum time algorithm on any input size. And so the only thing that is fixed is the input size. Okay. Another thing we sometimes consider is the average case. Okay. We always consider worst case. We sometimes consider average case. Okay, what is average case? Basically, it's the expected time of algorithm over all possible input of size. Okay, but because this is expected time, right? Expected time. So we need to know like the distribution of input. We know the distribution of input. Okay, because like some input happen more often than some other input, right? So we need to consider all different sort of input, but with the consideration of the probability distribution. Okay, so that's why we use the expected time. You guys have taken the probability, right? 那个几率统计有没有学过？是上学期学过的。谁教的？吴老师。Yeah. So you should be familiar with like expected time, right? Or expected something, right? Basically, that's when we say expected, that means average, right? Okay. This thing, I mean. Because you have taken the probability statistics this kind of classes. The third one, best case. We never consider this situation because it's useless. It's useless. Because, okay, for example, for the sorting algorithm, as I already told you, like if the input is already sorted, it is the quickest situation, right? Basically, okay, if you consider like the already sorted input, like that means you don't need to move any number anywhere other than its right or left. Then basically it takes if you think deeper, it takes only linear time. Okay, only take linear time, but it's useless. If these numbers are already sorted, why do you need to decide sorting algorithm in the first place? 如果你的数字都已经排好了，你设计排序有办法干嘛？发神经对不对？对。So that's why we say it's focus. It's useless. You cannot assume a certain input situation. That is useless. That is useless. So, as I said, worst case analysis, average case analysis are the ones that we consider in our class. Okay, in our class. In particular, worst case analysis is the most often to be considered. Okay, and also, okay, I keep using like running time, but actually, what we hear is not the real time. Why? Okay, because the real running time depends on what kind of machine you are using, right? Okay, if you are using like a PC, okay, it gives you like a good performance. But if you are using a computer like shouldn't say your grandma. Your grandma may not have a computer back to the old days. Okay. Then put it this way, okay. The first computer I used is called 小教授. At that time, that is Hong Xi. Okay. They produced a computer that only has like one line. Okay, one line. And it's not even graphical. It's like just like a text. Okay. And you can write basic. Okay, on that machine. So you can see how old I am, right? Yeah. This is a secret I revealed, just review. But anyway, so if the same program is running on that ancient computer, it's also a PC by the way. Okay, if the same program is run on that machine, obviously it will be like 100 times slower than the computer nowadays. Okay, so obviously the running time is dependent to your machine. Okay, so when we say worst case time, it depends on the speed of our computer. So we usually do not consider the absolute time. What we consider is the relative time. Okay, relative time on the same computer, on the same machine. We don't consider absolute time or absolute speed on different machines. That's useless. Okay, because like poor people buy like slower computer doesn't mean that the poor people cannot design good algorithm. So the idea is to we want to ignore machine-dependent constant. Okay, so we'll only look at the growth rate of Tn when n goes to infinity. Okay, this type of analysis is called a symptotic analysis. A symptotic analysis. So what is a symptotic analysis? Okay. So here comes, remember I told you like we have two different languages in algorithm. One is pseudocode, another one is more mathematical. Like big O, like theta, like those notation. So here, okay, the theta notation, theta here, it is f of n. Okay, there exists positive constant C1, C2, and N0 such that 0 small equal to C1 times G of n, small equal to f of n, small equal to C2 G of n, and for all n greater than equal to N0. First, this is like a formal definition of theta. And then also, by the way, if you still remember what you have learned from high school and your calculus, then you will notice that this notation is a set. This is a set notation, right? So when we say theta of Gn, actually what we are talking about is this is a set of functions. This is a set of functions. Okay. But in reality, okay, because we only have one student from math department, right? Okay. Yeah, 这个数学系的学生还在啊 ，OK，so try to forget where you are from, okay? Yeah, because like in the following, we are going to abuse the notation, okay? So mathematically, it is wrong, okay? It is like despicable, okay? But I mean, oh, by the way, my undergraduate major is also mathematics, okay? So it is when you are you come to computer science, you have to how should I say, like try to be more intuitive than how should I say, like then because mathematics is about formality, okay, very very formal stuff. You have to define everything like very clearly, and you try to divide things from one step to another. Yeah, this is like the training you learn from mathematics. But so when you are in a mathematics problem, you say, oh, this is a function. This is actually a set. This is a set. But actually, you will see like later on in our discussion, like we really are trying. Writing is really doesn't look like we are using that as a function, or as a set. So the engineering, the more intuitive way to deal with this, we just drop low order terms, ignore the leading constant. For example, 3n cubed plus 90n squared minus 5n plus 6,000 something. Okay, we just write it as theta n cubed. Okay, theta n cubed. And also, this is what I said. Remember, this is supposed to be a set, right? This is supposed to be a set. Okay. 如果你仔细想想看，这是一个集合啊。我觉得定义不是说这是一个集合吗？但是我们把它等于一个function哦。Something's wrong, right? Okay, but this is like engineering speaking. Like this is how we write it. Okay, if you are in mathematics department, your professor will give you a big X. Or in computer science, will give you a good grade. So what can I say? Yeah, just want you to know. Okay, basically in computer science, like we just consider like the highest order term and write that here. Okay, because we know this one, okay, this n cubed, okay, will satisfy this mathematical definition. Or put it another way, n cubed is one of the fn. Or you can put it another way to say it like one of the simplest fn choice. Okay, that satisfies this inequality. You can try to prove it. Okay, formally. Okay, but I will skip those like formal proof. But I suggest that you try to do it yourself. Okay, and this practice. Okay, once. So when we talk about asymptotic analysis, what we care is like when n gets large enough, okay, lower order, asymptotic growth, okay, always fits n cubed, like order always. So no matter what the lower order terms are, okay, as long as the leading term, okay, has a lower order, then the growth rate is going to be slower when n is large enough. Okay, so that's the concept of asymptotic performance analysis. Okay. how we consider in this class, but you know, so but in the real world situation, okay, the we shouldn't really ignore the lower order terms completely. Okay, so real world LV design often calls for a careful balance of engineering objectives. Okay, so a syntactic analysis is a useful tool to help us structure our thinking. But you know, if your lower order terms are too big, you know, well, some additional effort may be useful to cut it down a little. Okay? But just want you to understand why we consider a syntactic analysis, because eventually when A is big enough, when the problem size is big enough, okay, the higher order like meaning term will always cost you more time. But then it's big enough. So come back to the discussion in search and sort. Okay, what is worst case situation? Okay, it's when the input is the reverse order of the sorting situation, or is in a descending order. Okay, if the input is in, probably I can say it's also already sorted, but it's sorted in a descending situation. So if that's the case, think about that. Inserting the second number, and the first number still, if you have only one number, it must be sorted, right? When we insert the second number, you need to move the first number to the second place, and then put it in the first place. Put the second number in the first place. So it takes two moves, right? Inserting the third number, move the first two, one position to the right, and put it in the first place. So the third number takes 3 steps, and so on. So you can see then exactly what happens here, right? J start from 2. Okay, theta J. So you know this is like an arithmetic series. The summation order is theta n squared, right? So if it's n squared, it's pretty net, right? It's pretty net. So how about average case? The average case is, you know, of course, I mean, you need to consider all possible situations. But here, okay, let's try to play the lazy, okay? Because on average, okay, what is the best situation? The best situation is, you know, each one only need one comparison, right? The worst situation is like, like that, right? So average is exactly in between, right? In between. So let's just like use like add them up and divide by 2, right? Okay. So 第二个数字2 the second number is 2. Okay. So the second number here, I mean the best case is 1, right? So add them up, divided by 2. It's roughly J divided by 2, right? And third number and fourth number, so roughly it's J divided by 2. Okay? So if you do that, obviously it's also result in theta n squared. I mean, this one, obviously, the lower terms will be lower than this one, will be smaller than this one. But it is nevertheless still n squared. Still n squared. So you can see worst case, average case are both n squared. Okay. And remember, we do not consider the best case because it's useless, right? So insertion sort is insertion sort the best sorting algorithm. Well, in terms of a symptotic analysis, it is not. Or it is not. But if the n is small, it is relatively okay. Okay? But when n is large, it is bad. So okay? So let's take a 10 minutes break. When we come back, we'll continue the discussion for the reversal.